The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So we'll begin this time by looking at some probability distribution that you should be familiar with from this perspective. Starting with the Gaussian distribution for one variable. We're focused on a variable that takes real values in the interval minus infinity to infinity, and the Gaussian has the form exponential that is centered around some value, let's call it lambda, and has fluctuations around this value parameterized by sigma. And the integral of this p over the interval should be normalized to unity, giving you this hopefully very familiar form. Now, if we want to characterize the characteristic function, all we need to do is to Fourier transform this. So I have the integral dx e to the minus ikx. So this, let's remind you, alternatively was the expectation value of e to the minus ikx minus x minus lambda squared over 2 sigma squared, which is the probability distribution. And you should know what the answer to that is, but I will remind you we can change variables to x minus lambda being y. So from here, we will get a factor of e to the minus ik lambda. You have then the integral over y minus y squared over 2 sigma squared. And then what we need to do is to complete the square over here. And we can do that essentially by adding and subtracting a minus k squared sigma squared over 2. So that if I change variable to y plus I k sigma squared, let's call that z, then I have integral outside the integral e to the minus I k lambda minus k squared sigma squared over 2. And the remainder I can write as a full square. And this is just a normalized Gaussian integral that comes to 1. So as you well know, the Fourier transform of a Gaussian is itself a Gaussian, and that's what we've established, e to the minus I k lambda minus k squared sigma squared over 2. And if I haven't made a mistake, when I set k equals to 0, the answer should be 1, because k equals to 0, expectation value of 1, just amounts to normalization. Now, what we said was that a more interesting function is obtained by taking the log of this. So from here, we go to the log of p tilde of k. Log of p tilde of k is very simple for the Gaussian. And what we had said was that by definition, this log of the characteristic function generates cumulants through the series minus ik to the power of n over n factorial, the nth cumulant. So looking at this, we can immediately see that the Gaussian is characterized by a first cumulant, which is the coefficient of minus ik. It's lambda. It is characterized by a second cumulant, which is the coefficient of minus ik squared. This, is the variance, and we can explicitly see that the coefficient of minus ik squared over 2 factorial is simply sigma squared. So this is repetition. But one thing that is interesting is that our series has now terminates, which means that if I were to look at the third cumulant, if I were to look at the fourth cumulant, and so forth, for the Gaussian, they're all 0. So the Gaussian is the distribution that is completely characterized just by its first and second cumulants, all the rest being 0. Okay? So now last time, we developed some kind of a graphical method. We said that I can graphically describe the first cumulant as a bag with one point in it, second cumulant with something that has 2 points in it, third cumulant with 3, fourth cumulant with 4, and 4 points, and so forth. Okay? This is just rewriting. Now, the interesting thing was that we said that the various moments we could express graphically, so that, for example, the second moment is either this or this, which then graphically is the same thing as lambda squared plus sigma squared, because this is indicated by sigma squared. Now, x cubed, you would say, is either 3 things by themselves, or put 2 of them together and then 1 separate, and this I could do in 3 different ways. And in general, for a general distribution, I would have had another term, which is a triangle. But the triangle is 0. So for the Gaussian, this terminates here. I have lambda cubed plus 3 lambda sigma squared. If I want to calculate x to the 4th, maybe the old way of doing it would have been to multiply the Gaussian distribution against x to the 4th and try to do the integration. And you would ultimately be able to do that by rearranging things and looking at various powers of the Gaussian integrated from minus infinity to infinity. But you can do it graphically. You can say, OK, it's either this, or I can have, well, I cannot put 1 aside and 3 together because that doesn't exist. I could have 2 together and 2 not together. And this I can do in 6 different ways. You can convince yourself of that. Or I could do 2 pairs, which I can do 3 different ways, because I can either do 1, 2, 1, 3, 1, 4, and then the other is satisfied. So this is lambda to the 4th plus 6 lambda squared sigma squared plus 3 sigma to the 4th. And you can keep going and doing different things. OK? Question? Yeah?
The second cumulant supposed to be squared?
Where?
Because so you said that the second
Oh.
cumulant of x squared, yes.
This, so that's the wrong. The coefficient of k squared is the second cumulant. The additional 2 was a mistake. Okay. Anything else? All right. Let's take a look at a couple of other distributions, this time discrete. So the binomial distribution is repeat a binary random variable. And what does this mean? Means two outcomes that's binary. Let's call them A and B. And if I have a coin that's head or tails, it's binary with two possibilities, and I can assign probabilities to the two outcomes to be PA and PB, which has to be 1 minus PA. And the question is, if we repeat this binary random variables n times, what is the probability of NA outcomes of A? And I forget to say something important, so I write it in red. These should be independent. That is, the outcome of a coin toss at, say, the 5th time should not influence the 6th time and future times. So, okay, so this is easy. The probability to have NA occurrences of A in n trials, so it has to be indexed by n, is that within the n times that I tossed, A came up NA times. So it has to be proportional to the probability of A independently multiplied by itself NA times. But if I have exactly NA occurrences of A, all the other times I had B occurring. So I have the probability of B for the remainder, which is n minus NA. Now, this is the probability for a specific occurrence. Like the first NA times that I threw the coin, I will get A. The remaining times I would get B. But the order is not important. And the number of ways that I can shuffle the order and have a total of NA out of n times is the binomial factor. Okay. Fine. Again, well known. Let's look at its characteristic function. So P tilde, which is now a function of k, is expectation value of e to the minus I, k, and a, which means that I have to weigh e to the minus I, k, and a against the probability of occurrences of NA times, which is this binomial factor. PA to the power of NA, PB to the power of n minus NA. And of course, I have to sum over all possible values of NA that go all the way from 0 to n. Okay? So what we have here is something which is this combination, PA e to the minus ik raised to the power of NA, PB raised to the complement n minus NA, multiplied by the binomial factor, summed over all possible values. So this is just the definition of the binomial expansion of PA e to the minus ik plus PB raised to the power of n. Okay? And again, let's check. If I set k equals to 0, I have PA plus PB, which is 1 raised to the power of n. So things are OK. So this is the characteristic function. At this stage, the only thing that I will note about this is that if I look at the characteristic function, I will get n times. So this is actually, let's make sure that we maintain the index n. So this is the characteristic function appropriate to n trials. And what I get is that up to factor of n, I will get the characteristic function that would be appropriate to one trial. Okay. So what that means, if I were to look at powers of k, the expectation value of some cumulant, if I were to repeat things n times, so this carries an index n, is going to be simply n times what I would have had in a single trial. So for a single trial, you really have two outcomes, 0 or 1 occurrences of this object. So for a binary variable, you can very easily compute these quantities, and then you can calculate the corresponding ones for n trials, simply multiplying by n. And we will see that this is characteristic, essentially, of anything that is repeated n times, not just the binomial. So this form that you have n independent objects, you would get n times what you would have for one object, is generally valid, and actually something that we will build a lot of statistical mechanics on, because we are interested in the limit of large n. So we'll see that shortly. But rather than following this, let's look at a third distribution that is closely related, which is the Poisson. And the question that we are asking is, we have an interval, and the question is, what is the probability of m events in an interval from 0 to t. And I kind of express it this way because the prototypical Poisson distribution is, let's say, the radioactivity. And you can be waiting for some time interval from 0 to 1 minute and asking within that time interval, what's the probability that you will see m radioactive decay events? So what is the probability if two things happen? One is that the probability of one and only one event in interval dt is alpha dt as dt goes to 0. Okay, so basically, if you look at this over 1 minute, the chances are that you will see so many events, so many radioactivities. If you shorten the interval, the chances that you would see events would become less and less. If you make your event infinitesimal, most of the time nothing would happen. With very small probability that vanishes as the size of the interval goes to 0, you will see one event. So this is one condition, and the second condition is events in different intervals are independent. And since I wrote independent in red up there, let me write it in red here, because it sort of harks back to the same condition. And so this is the question. What is this probability? And to get the answer, what we do is to subdivide our big interval into n, which is big T divided by d small dt subintervals. So basically, originally, let's say, on the time axis, we were covering a distance that went from 0 to big T, and we were asking what happens here. So what we are doing now is we are sort of dividing this interval to lots of subintervals, the size of each one of them being dt, and therefore the total number is big T over dt. And ultimately, clearly, I want to set dt going to 0 so that this condition is satisfied. So also because of the second condition, each one of these will independently tell me whether or not I have an event. And so if I want to count the total number of events, I have to add things that are occurring in different intervals. And we can see that this problem now became identical to that problem, because each one of these intervals has two possible outcomes. Nothing happens with probability 1 minus alpha dt. Something happens with probability alpha dt. So no event with probability 1 minus alpha dt, one event with probability alpha dt. So this is a binomial process. Okay? So we can calculate, for example, the characteristic function. And I will indicate that we are looking at some interval of size t and parameterized by this rate alpha. We'll see that only the product will occur. So this is the Fourier variable. We said that it's a binary, so it is one of the probabilities plus e to the minus ik plus the other probability raised to the power of n. Now we just substitute the probabilities that we have over here. So the probability of not having an event is 1 minus alpha dt. The probability of having an event is alpha dt. So alpha dt is going to appear here as e to the minus ik minus 1. So alpha dt e to the minus ik is from here. From PB, I will get 1 minus alpha dt. And I bunch together the two terms that were proportional to alpha dt. And then I have to raise to the power of n, which is t divided by dt. And this whole prescription is valid in the limit where dt is going to 0. So what you have is 1 plus an infinitesimal raised to a huge power. And this limiting procedure is equivalent to taking the exponential. So basically, this is the same thing as exponential of what is here multiplied by what is here. The dt's cancel each other out. And the answer is alpha t e to the minus ik minus 1. So the characteristic function for this process that we described is simply given by this form. You say, wait, I didn't ask for the characteristic function. I wanted the probability. Well, I say, OK, characteristic function is simply the Fourier transform. So let me Fourier transform back. And I would say that the probability along not the Fourier axis, but the actual axis is obtained by the inverse Fourier process. So I have to do an integral dk over 2 pi e to the ikx times the characteristic function. And the characteristic function is e to the minus what was it, e to the alpha t, e to the minus ik minus 1. Okay? Well, there is an e to the minus alpha t that I can simply take outside the integration. I have the integration over k e to the I kx. And then what I will do is I have this factor of e to the something in the e to the alpha t e to the minus ik. I will use the expansion of the exponential. So the expansion of the exponential is a sum over m running from 0 to infinity, the exponent raised to the mth power. So I have alpha t raised to the mth power e to the minus ik raised to the mth power divided by m factorial. Okay? So now I reorder the sum and the integration. The sum is over m, the integration is over k. I can reorder them. So on the things that go outside, I have a sum over m running from 0 to infinity, e to the minus alpha t to the power of m divided by m factorial. And then I have the integral over k over 2 pi e to the I k. Well, I had the x here, and I have e to the minus I k m here. So I have x minus m. Okay? And then I say, OK, this is an integral that I recognize. The integral of e to the I k times something is simply a delta function. So this whole thing is a delta function that says, oh, x has to be an integer. Because I kind of did something that maybe in retrospect you would have said, why are you doing this? Because along how many times things have occurred, they have either occurred 0 times, 1 times, 2 decays, 3 decays. I don't have 2.5 decays. So I treated x as a continuous variable, but the mathematics was really clever enough to say that no, the only places that you can have are really integer values. And the probability that you have some particular value, integer m, is simply what we have over here, e to the minus alpha t to the power of m divided by m factorial, which is the Poisson distribution. Okay. But fine, so this is the Poisson distribution, but really we go through the root of the characteristic function in order to use this machinery that we developed earlier for the cumulants, etc. So let's look at the cumulant generating function. So I have to take the log of the function that I had calculated there. It is nicely in the exponential, so I get alpha t e to the minus ik minus 1. So now I can make an expansion of this in powers of k. So I can expand the exponential. The first term vanishes because this starts with 1. So really I have alpha t, some running from 1 to infinity, or n running from 1 to infinity, minus ik to the power of n over n factorial. Right? So my task for identifying the cumulants is to look at the expansion of this log and read off powers of minus ikn to the power of n factorial. So what do we see? We see that the first cumulant of the Poisson is alpha t, but all the coefficients are the same thing. the expectation value, the second cumulant is alpha t, the third cumulant, the fourth cumulant, all the other cumulants are also alpha t. Okay? So the average number of decays that you see in the interval is simply alpha t. But there are fluctuations, and if somebody should, for example, ask you what's the average number cubed of events, you would say, okay, I'm going to use the relationship between moments and cumulants. I can either have 3 first objects, or I can put one of them separate in 3 different fashions. But this is a case where the triangle is allowed. So diagrammatically, all 3 are possible. And so the answer for the first term is alpha t cubed. For the second term is a factor of 3. Both the variance and the mean give me a factor of alpha t, so I will get alpha t squared. And the third term, which is the third cumulant, is also alpha t. So the answer is simply of this form. Okay? Again, m is an integer, alpha t is dimensionless, so there is no dimension problem with having different powers. Okay? Any questions? All right, so that's what I wanted to say about one variable. Now let's go and look at corresponding definitions when you have multiple variables. So for many random variables, the set of possible outcomes, let's say, has variables x1, x2. Let's be precise. Let's end it at xn. And if these are distributed, each one of them continuously over the interval, to each point, we can characterize some kind of a probability density. So this entity is called the joint probability density function. And its definition would be to look at probability of outcome in some interval that is between, say, x1 plus dx1 in one, x2 plus dx2 in the second variable, xn plus dxn in the last variable. So you sort of look at a particular point in this multi-dimensional space that you are interested. You build a little cube around it. You ask what's the probability to be in that cube, and then you divide by the volume of that cube. So dx1, dx2, dxn, which is the same thing that you would be doing in constructing any density by ultimately taking the limit that all of the dx's go to 0. Okay? Fine. So this is the joint probability distribution. You can construct now the joint characteristic function. How do you do that? Well, again, just like you would do Fourier transform with multiple variables. So you would go for each variable to a conjugate variable. So x1 would go to k1, x2 would go to k2, xn would go to kn. And this would mathematically amount to calculating the expectation value of e to the minus I, k1 x1, k2 x2, and so forth. Which you would obtain by integrating over all of these variables, e to the minus I k alpha x alpha against the probability of x1 to xn. Question?
It's a bit hard to read. Getting really small.
Okay. But it's just multidimensional integral. Okay? All right? So this is, as the case of 1, I think your problem is not the size, but the angle. I see. I can't do much with that. You have to move to the center. OK, so what we can look at now is joint moments. Right? So you can, when we had one variable, we could look at something like the expectation value of x to the m. That would be the mth moment. But if we have two variables, we can raise x1 to some power, x2 to another power, and actually xn to another power. So this is a joint moment. Okay? Now the thing is that the same way that moments for one variable could be generated by expanding the characteristic function, if I were to expand this function in powers of k, you can see that within the expectation value, I will get various powers of x1 to some power, x2 to some power, etc. So by appropriate expansion of that function, I can generate all of, or read off all of these moments. Now, a more common way of generating the Taylor series expansion is through derivatives. So what I can do is I can take a derivative with respect to, say, ik1. If I take a derivative with respect to ik1 here, what happens is I will bring down a factor of minus x alpha. So actually, let me put the minus, so it becomes a factor of x alpha. And if I integrate x alpha against this, I will be generating the expectation value of x alpha, provided that ultimately I set all of the k's to 0. So I will calculate a derivative of this function with respect to all of these arguments. At the end of the day, I will set k equals to 0. That would give me the expectation value of x1. But I don't want x1. I want x1 raised to the power of m1. So I do this. Each time I take a derivative with respect to minus ik, I will bring down a factor of the corresponding x. And I can do this with multiple different things. So d by di k2 raised to the power of m2 minus d by di kn, the whole thing raised to the power of mn. So I can either take this function of multiple variables, k1 through kn, and expand it and read off the appropriate powers of k1, k2, or I can say that the terms in this expansion are generated through taking the appropriate derivatives. Yes?
Is there any reason why you're choosing to take a derivative with respect to ikj instead of simply putting I in the numerator, or are there other things that I'm not?
No, there is no reason. So you are saying, why didn't I write this as this, like this, I divided? I think I just visually saw that it was kind of more that way, but it's exactly the same thing, yes. Okay. All right. Now, the interesting object, of course, to us is more the joint cumulants. Okay. So how do we generate joint cumulants? Well, previously, essentially, we had a bunch of objects for one variable that was some moment. And in order to make them cumulants, we just put a sub c here. So we do that, and we are done. But what did operationally happen was that we did the expansion rather than for the characteristic function, for the log of the characteristic function. So all I need to do is to do precisely this set of derivatives applied rather than to the joint characteristic function to the log of the joint characteristic function. And at the end, set all of the k's to 0. Okay. So by looking at these two definitions and the expansion of the log, for example, you can calculate various things, like, for example, x1, x2 with a c is the expectation value of x1, x2, this joint moment minus x1, x2, just as you would have thought would be the appropriate generalization of the variance, and this is the covariance. And you can construct appropriate extensions. Okay? Now, we made a lot of use of a relationship between moments and cumulants. So the idea really was that the essence of a probability distribution is characterized in the cumulants. Moments kind of depend on how you look at things. The essence is in the cumulants, but sometimes the moments are more usefully computed, and there was a relationship between moments and cumulants. We can generalize that graphical relation to the case of joint moments and joint cumulants. So graphical relation applies as long as points are labeled by appropriate or by corresponding variable. Okay, so suppose I wanted to calculate some kind of a moment that is x1 squared, let's say x2, x3. This may generate for me many diagrams, so let's stop from here. Okay? So what I can do is I can have points that I label 1, 1, and 2, and have them separate from each other. Or I can start pairing them together. So one possibility is that I put the 1s together and the 2 start separately. Another possibility is that I can group the 1 and the 2 together, and then the other one starts separately. But I had a choice of 2 ways to do this. So this diagram with an overall factor of 2. And then there is the possibility to put all of them in the same bag. And so mathematically, that means that the third, this particular joint moment is obtained by taking average of x1 squared x2, average, which is the first term. The second term is the variance of x1, and then multiplied by x2. The third term is twice the covariance of x1 and x2 times the mean of x1. And the final term is just the third cumulant. So again, you would need to compute these presumably from the log of the characteristic function, and then you would be done. Couple of other definitions. One of them is an unconditional probability. So very soon we will be talking about, say, probabilities appropriate to the gas in this room, and the particles in the gas in this room will be characterized by where they are, some position vector q, and how fast they are moving, some momentum vector p. And there would be some kind of a probability density associated with finding a particle with some momentum at some location in space. But at some point I say, well, I really don't care about where the particles are. I just want to know how fast they are moving. So what I really care is the probability that I have a particle moving with some momentum p, irrespective of where it is. Then all I need to do is to integrate over the position the joint probability distribution. And the check that this is correct is that if I were to now integrate this over p, this would be integrated over the entire space, and the joint probability is appropriately normalized so that the joint integration will give me 1. So this is a correct normalized probability. And more generally, if I'm interested in, say, a bunch of coordinates x1 through xs, out of a larger list of coordinates that spans x1 through xs all the way to something else, all I need to do to get the unconditional probability is to integrate over the variables that I'm not interested. Again, check is that it's a good, properly normalized. Now this is to be contrasted with the conditional probability. The conditional probability, let's say we would be interested in calculating the pressure that is exerted on the board. The pressure is exerted by the particles that impinge on the board and then go away. So I'm interested in the momentum of particles right at the board, not anywhere else in space. So if I'm interested in the momentum of particles at a particular location, which could in principle depend on location, so now Q is a parameter, P is the variable, but the probability distribution could depend on Q. How do we obtain this? this again is going to be the proportional to the probability that I will find a particle both at this location with momentum p. So I need to have that. But it's not exactly that. There is a normalization involved. And the way to get normalization is to note that if I integrate this probability over its variable p, but not over the parameter q, the answer should be 1. So this is going to be, if I apply it to the right-hand side, the integral over p of p and q, which we recognize as an example of an unconditional probability to find something at position q. So the normalization is going to be this, so that the ratio is 1. So most generally, we find that the probability to have some subset of variables, given that the location of the other variables in the list are somewhat fixed, is given by the joint probability of all of the variables, x1 through xn, divided by the unconditional probability that applies to the parameters that are fixed. And this is called Bayes' theorem. Okay. By the way, if variables are independent, which actually does apply to the case of the particles in this room as far as their momentum and position is concerned, then the probability, the joint probability, is going to be the product of one that is appropriate to the position and one that is appropriate to the momentum. And if you have this independence, then what you find is that there is no difference between conditional and unconditional probabilities. And when you go through this procedure, you will find that all the joint cumulants, but not the joint moments, naturally, all the joint cumulants will be 0. Okay, any questions? Yes?
Could you explain how that condition of p...
How this was obtained? Or the one above?
Yeah, the condition that you applied that the integral is 1.
Okay. So first of all, what I want to look at is the probability that is appropriate to one random variable at a fixed value of all the other random variables. Like you say, in general, I should specify the probability as a function of momentum and position throughout space, but I'm really interested only at this point. I don't really care about other points. However, the answer may depend whether I'm looking at here or I'm looking at here. So the answer for the probability of momentum is parameterized by Q. On the other hand, I say that I know the probability over the entire space to be at this position with the momentum P is given by this joint probability. But if I just set that equal to this, the answer is not correct, because the way that this quantity is normalized is if I were to integrate over all possible values of its variable P, the answer should be 1, irrespective of what Q is. So I can define a conditional probability for momentum here, a conditional probability for momentum there. In both cases, the momentum would be the variable, and integrating over all possible values of momentum should give me 1 for a properly normalized probability distribution.
Given any condition of p
given that Q is something. So Q could be some, not here, Q can be regarded as some parameter. So the condition is that this integration should give me 1. I said that on physical grounds, I expect this conditional probability to be the joint probability up to some normalization that I don't know. Okay, so what is that normalization? The whole answer should be 1. What I have to do is an integration over momentum of the joint probability. I have said that an integration over some set of variables of a joint probability will give me the unconditional probability for all the others. So integrating over all momenta of this joint probability will give me the unconditional probability for position. So the normalization of 1 is the unconditional probability for position divided by n. So n, this has to be this. And in general, it would have to be this in order to ensure that if I integrate over this first set of variables of the joint probability distribution, which would give me the unconditional, cancels the unconditional in the denominator to give me 1. Okay? Other questions? Okay? So I'm going to erase this last board to be underneath that top board in looking at the joint Gaussian distribution. So that was the Gaussian, and we want to look at the joint Gaussian. Okay. So we want to generalize the formula that we have over there for one variable to multiple variables. Okay. So what I have there initially is a factor which is exponential of minus 1/2 x minus lambda squared. I can write this x minus lambda squared as x minus lambda, x minus lambda, and then put the variance, let's call it 1 over, okay, sigma rather than a small sigma squared or something like this. Actually, let me just write it as 1 over sigma squared for the time being. And then the normalization was 1 over root 2 pi sigma squared. Okay. But you say, well, I have multiple variables, so maybe this is what I would give for my nth variable. And then I would sum over all n running from 1 to n. So this is essentially the form that I would have for n independent Gaussian variables. And then I would have to multiply here factors of 2 pi sigma squared. So I would have 2 pi to the n over 2. Then I would have product of, well, actually, let's write it as 2 pi to the n square root. I would have the product of sigma I squared. Okay? But that's just too limiting a form. The most general form that is quadratic will allow me to have also cross terms where it is not only the diagonal terms x1 and x1 that are multiplying each other, but x2 and x3, etc. So I would have a sum over both m and n running from 1 to n. And then the coefficient here, rather than just being a number, would be the variables that would be like a matrix, because for each pair m and n, I would have some number, and I will call them the inverse of some matrix C. Okay? And if you again think of the problem as a matrix, if I have the diagonal matrix then the product of elements along the diagonal is the same thing as the determinant. If I were to rotate the matrix to have off-diagonal elements, the determinant will always be there. So this is really the determinant of C that will appear here. Yes?
So are you inverting the individual elements of C, or are you inverting the matrix C and taking its elements?
Actually, a very good point. I really wanted to write it as the inverse of the matrix and then pick the n-mth elements. So we imagine that we have a matrix, and these are the elements of some. So I could have called this whatever I want. So I could have called the coefficients xmn. I have chosen to regard them as the inverse of some other matrix C. And the reason for that becomes shortly clear, because the covariances will be related to the inverse of this matrix, and hence that's the appropriate way to look at it.
What C means again?
Okay, so let's forget about the lambdas. So I would have, in general, for two variables, some coefficient for x1 squared, some coefficient for x2 squared, and some coefficient for x1, x2. Okay, so I could call this A11, I could call this A22, I could call this 2A12, or actually I could, if I wanted, just write it as A12 plus A21 x2 x1, although A12 and A21 would be the same. So what I could then regard this is as x1, x2, the matrix A11, A12, A21, A22, x1, x2. So this is exactly the same as that, right? So these objects here are the elements of this matrix C inverse. So I could call this x1, x2, some matrix A, x1, x2, where A is a 2 by 2 matrix. The name I have given to that 2 by 2 matrix is C inverse. Yes?
The matrix is required to be symmetric, though, isn't it?
The matrix is required to be symmetric for any quadratic form, yes. So when I wrote it initially, I wrote as 2A12, and then I said, well, I can also write it this fashion, provided the two of them are the same. Yes?
How did you know the determinant of C belongs there?
Pardon?
How did you know that the determinant of C?
Okay. How do I know a determinant of C? Let's say I give you this form, and then I don't know what the normalization is. What I can do is I can do a change of variables from x1, x2 to something like y1, y2, such that when I look at y1 and y2, the matrix becomes diagonal. So I can rotate the matrix. So any matrix, I can imagine that I will find some u such that A, u dagger is this diagonal matrix lambda. Now, under these procedures, one thing that does not change is the determinant. It's always the product of the eigenvalues. The way that I set up the problem, I said that if I hadn't made the problem to have cross terms, I knew the answer to be the product of the eigenvalues. So if you like, I can start from there and then do a rotation and have the more general form. The answer would stay as the determinant. Yes? The matrix should be positive definite in order for the probability to be well defined and exist. Yes. Okay. So if you like, by stating that this is a probability, I have imposed a number of conditions such as symmetry as well as positivity. Yes. Okay. But this is just linear algebra. I will assume that you know linear algebra. Okay, so this is properly normalized Gaussian joint probability. We are interested in the characteristic function. So what we are interested is the joint Gaussian characteristic. And so again, we saw the procedure was that I have to do the Fourier transform. Okay. So I have to take this probability that I have over there and do an integration product, say, alpha running from 1 to n dx alpha of e to the minus I k alpha x alpha. This product exists for all values. Then I have to multiply with this probability that I have up there. It should appear here. Okay? Now, again, maybe an easy way to imagine is what I was saying to you previously. Let's imagine that I have rotated into a basis where everything is diagonal. Then in the rotated basis, all you need to do is to essentially do product of characteristic functions such as what we have over here. So the corresponding product to this first term would be exponential of minus I, sum over n running from 1 to n, k alpha lambda alpha, k n lambda n. I guess I'm using n as the variable here. And as long as things would be diagonal, the next order term would be a sum over alpha kn squared, the corresponding eigenvalue inverted. Right? So remember that in the diagonal form, each one of these sigmas would appear as the diagonal. If I do my rotation, essentially this term would not be affected. The next term would give me minus 1/2 sum over m and n, rather than just having k1 squared, k2 squared, etc. Just like here, I would have km, kn. What happened previously was that each eigenvalue would get inverted. If you think about rotating a matrix, all of its eigenvalues are inverted, you are really rotating the inverse matrix. So this here would be the inverse of whatever matrix I have here. So this would be Cmn. So I will leave you to do the corresponding linear algebra here, but the answer is correct. So the answer is that the generator of cumulants for a joint Gaussian distribution has a form which has a bunch of linear terms, kn lambda n, and a bunch of second order terms. So we will have minus 1/2 sum over m and n, km, kn, times some coefficients. Okay? And the series terminates here. So for the joint Gaussian, you have first cumulants. So the expectation value of xn cumulant is the same thing as lambda m. You have covariances or second cumulants, xm, xn, c is cmn. And in particular, the diagonal elements would correspond to the variances. And all higher orders are 0. Because there is no further term in the expansion. Okay? So for example, if I were to calculate this thing that I have on the board here for the case of a Gaussian, for the case of the Gaussian, I would not have this third term. So the answer that I would write down for the case of the third term would be something that didn't have this. And in the way that we have written things, the answer would have been x1 squared x2 would be just lambda 1 squared lambda 2 plus lambda 1, plus sigma 1 squared, or let's call it C11, times lambda 2 plus 2 lambda 1 C12, and that's it. Okay? So So there is something that follows from this that is used a lot in field theory, and it's called Wick's theorem. So it's just a particular case of this, but let's state it anyway. So for Gaussian distributed variables of zero mean, following condition applies. I can take the first variable raised to the power n1, the second variable to n2, the last variable to some power nn, and look at a joint expectation value such as this. And this is 0 if sum over alpha and alpha is odd, and is called sum over all pairwise contraction if sum over alpha and alpha is even. Okay. So actually, I have right here an example of this. If I have a Gaussian variable, jointly distributed Gaussian variables where the means are all 0. So if I say that lambda 1 and lambda 2 are 0, then this is an odd power, x1 squared x2. Because of the symmetry, it has to be 0, but you explicitly see that every term that I have will be multiplying some power of lambda. Whereas if rather than this, I was looking at something like x1 squared x2 x3, where the net power is even, then I could sort of imagine putting them into these kinds of diagrams, or alternatively, I can imagine pairing these things in all possible ways. So one pairing would be this with this, this with this, which would have given me x1 squared c, x2 x3c. Another pairing would have been x1 with x2, and then naturally x1 with x3. So I would have gotten x1 with x2 covariance, x1 with x3 covariance. But I could have connected the first x1 to x2, or the second x1 to x2. So this comes in two variants. And so the answer here would be C11, C23, plus 2, C12, C13. Yes?
correspond to the n-log next to the answer. This should be the cumulant, right? Or is it the moment?
This is the moment.
Okay.
The contractions are the covariances.
Okay.
So the point is that the Gaussian distribution is completely characterized in terms of its covariances. Once you know the covariances, essentially you know everything. And in particular, you may be interested in some particular combination of x's, and then you use to express that in terms of all possible pairwise contractions, which are the covariances. And essentially, in all of field theory, you expand around some kind of a Gaussian background or Gaussian zeroth order result. And then in your perturbation theory, you need various powers of your field or some combination of powers, and you express them through these kinds of relationships. Okay? Any questions? Okay. This is fine. Let's get rid of this. Okay. Now, there is one result that all of statistical mechanics hangs on. So I expect that as I get old and I get infirm or whatever and my memory vanishes, the last thing that I will remember before I die would be this central limit theorem. Okay? And why is it this important is because you end up in statistical physics adding lots of things. So really the question that we have, or you should be asking, is thermodynamics is a very precise thing. It says that heat goes from the higher temperature to lower temperature. It doesn't say it does that 50% of the time or 95% of the time. It's a definite statement. If I'm telling you that ultimately I'm going to express everything in terms of probabilities, how does that jibe? The reason that it jibes is because of this theorem. It's because in order to go from the probabilistic description, you will be dealing with so many different, so many large number of variables that probabilistic statements actually become precise deterministic statements. And that's captured by this theorem, which says that let's look at the sum of n random variables. And I will indicate the sum by x and my random variables as small x's. And let's say that there is, for the individual set of things that I'm adding up together, some kind of a joint probability distribution out of which I take these random variables. So each instance of this sum is selected from this joint PDF. So x itself is a random variable because of possible choices of different xi from this probability distribution. Okay? So what I'm interested is what is the probability for the sum. So what is the p that determines this sum? Okay? I will go by the root of these characteristic functions. I will say, okay, what's the expectation value of, what's the Fourier transform of this probability distribution? Okay, Fourier transform, by definition, it is the expectation value of e to the minus ik, this big X, which is the sum over all of the small x's. Okay, do I have that definition somewhere? I erased it. Basically, what is this? If this k was in fact different k's, if I had a k1 multiplying x1, k2 multiplying x2, that would be the definition of the joint characteristic function for this joint probability distribution. So what this is you take the joint characteristic function, which depends on k1, k2, all the way to kn, and you set all of them to be the same. Right? So take the joint characteristic function depends on n Fourier variables, put all of them the same k, and you have that is for the sum. Okay? So I can certainly do that by adding a log here. Nothing has changed. I know that the log is the generator of the cumulants. So this is a sum over, let's say, n running from 1 to infinity minus ik to the power of n over n factorial, the joint cumulants of the sum. Right? Okay. So what is the expansion that I would have for log of the joint characteristic function? Well, typically I would say have at the lowest order k1 times the mean of the first variable, k2 times the mean of the second variable, but all of them are the same. So the first order I would get minus I the same k sum over n of the first cumulant of the nth variable. Okay? Typically, the second order term, I would have all kinds of products. I would have k1, k3, k2, k4, as well as k1 squared. But now all of them become the same. And so what I will have is a minus ik squared. But then I have all possible pairings, mn of xm, xn cumulants.
Question.
Yes.
Writing down this expression, you probably should use different indices when you're summing over elements of Taylor series and when you're summing over your n random variables. Just it gets confusing when both indices are n.
This here, you want me to write here, say I.
Yes, absolutely.
Okay. And here I can write I and j. Right. So I think there's still a 2 factorial. And then there's higher orders. Essentially, then matching the coefficients of minus ik from the left and minus ik from the right will enable me to calculate relationships between cumulants of the sum and cumulants of the individual variables. This first one of them is not particularly surprising. You would say that the mean of the sum is sum of the means of the individual variables. Okay? The second statement is that the variance of the sum really involves a pair I and j running from 1 to n. So if these variables were independent, you would be just adding the variances. Since they are potentially dependent, you have to also keep track of covariances. And this kind of summation extends to higher and higher cumulants, essentially including more and more powers of cumulants that you would put on that side. Okay? And what we do with that, I guess we'll start next time around.